So in the next problem, we have a situation where you have a concentration of oxygen in a fixed volume of water. So it says, suppose a small pond normally contains 12 units of dissolved oxygen in a fixed volume of water. And suppose at time zero, a little bit of organic waste is introduced into the pond with an oxygen concentration T weeks later given by, so this is oxygen concentration. That's supposed to be a 2. And if we did a little algebraic manipulation, which I think most of you got to this point right here, we were going to do it when we're looking at the limit as t approaches infinity. We want to know what happens to this long term. And I think most people realized that what you'd have to do was to multiply top and bottom by 1 over t squared, because that's the highest order in the denominator.
Where'd you get the squares?
Oh, sorry. Okay. So you multiply this by 1 over t squared times 1 over t squared, right? And when you multiply this t squared into each 1 over t squared into each of those terms, so we're going to have 12 t squared times 1 over t squared. We're going to have minus 15t times 1 over t squared. And we're going to have 12 times 1 over t squared, right? And then down here we're going to have t squared times 1 over t squared plus 1 times 1 over t squared. So let's simplify that. We're going to have the limit as t goes to infinity of 12 minus 15 over t plus 12 over t squared all over 1 plus 1 over t squared. I think I still have a... No. So, as I take t going to infinity, anything with t in the denominator, those denominators are going to get really huge. That means the whole fraction is going to get really small and close to 0, right? So anything with t in the denominator is going to go to 0.
And that's because it's the limit infinity.
Because we're taking the limit as the input goes to infinity, yes. Yes, it's one of those special sequences. Okay, so all I'm left with is 12 over 1, right? So the answer is 12. Okay, now, I think most of you got to that point. The second part of the question asks you, will the oxygen level ever return to 12? Think very carefully about this. Think very carefully about this. As you're inputting different times, you're going to get closer and closer to 12, granted. But are you actually going to ever get there?
No.
No. Think about this, and I'll give you the explanation in terms of a different problem. This is a story that, I mean, you can tell I grew up in a mathy family. This is a story my dad told me when I was yay big trying to go to sleep. There's a tortoise and a hare. Now, this is a little different than the story you might have heard. They have a race. You know, the tortoise is like, I don't want to race you, hare. You always win. And he's like, well, this time you set the rules. Okay, that's fine. I got the rules. The rules are, hare, you can go as fast as you want, But every time you get halfway to the finish line, you got to stop for 1 second, take a breath, and then go halfway again. Stop 1 second, take a breath. Okay. And the hare's like, no problem. 1 second pauses, I'm still going to beat you. Okay, so who won? Why?
Because the rabbit never gets to the finish line. He never gets to it, because if you always have to stop halfway, there's always a halfway point
Yeah.
of anything.
He never actually gets there. This is the essence of radioactive decay. Every half-life, you're going to pull out half and turn it into a different isotope. Are you ever going to actually get rid of it completely? Not in theory, because there's always half left. This is the same idea with the oxygen concentration. As you start to pull one type into another, there's always going to be some left if you're just pulling out a fraction, right? So this is how limits work. It's a limit. You're going to reach there in infinite time. But are we ever going to see it? Unlikely. Now that's on an atom level, okay? That's on there's so many atoms in a pond, okay, right? If we were really dealing with a population of 8, and I pulled out half every time, eventually I'm going to get to 1, and then I'm going to have to figure out, okay, does that rule mean that I'm going to pull that last one? But we're here talking about atoms. That's infinitely abundant. And the idea is that there'll always be something left in finite time. Take infinite time to reach 0. Okay? So technically the answer here is no. Okay?